You might ask yourself, what are you doing at an OSGi conference? So actually, way back, I think 9 years ago, I was doing a PhD on distributed computing, and then OSGi was kind of spot on. They were developing the remote services over then. That's also how I became involved in the Alliance. I became an invited contributor working on a few specs, which resulted in the R7 cluster info spec. But then later on, our team changed focus. We moved towards from distributed systems to distributed AI, towards AI for robotics. And the OSGi standard just kept following me along because it was just like the best development model I had until then to do stuff. So I kept on using it. And right now I'm at the point that I think, yeah, looking to OSGi from an AI perspective, maybe there are some goodies in there that are worth sharing. So that's where this talk is all about. So let's first pin down what AI is really about. So AI is basically the next big thing, but of course, after blockchain. So it's kind of a hype term nowadays where everybody wants to do AI, everyone needs some AI in their product, but nobody really pins down what they actually mean with that. And if you really talk to the use cases people have, then probably you end up that it's actually just machine learning, which is kind of a subset of the whole AI domain, where you take a model, which is usually just a black box model with lots of knobs that you can twist and tune, and then you give it some inputs and the desired outputs, and then you turn your knobs until your outputs kind of match the desired outputs for the inputs you have, and then you hope that magically this will generalize to the whole world, and you basically have a nice model that can map any input to your desired outputs. You also often heard the term deep learning nowadays, and this is basically just the same, but then you switch the black box with a neural network. And neural networks prove to be very good at processing high-dimensional inputs like images or text or sound. And I deliberately took this picture because I think it's very important to know that in the end, your neural network is no more than just a pattern recognizer, and that is tuned to recognize certain patterns that you fed into it. So if you give it lots of pictures of cats, then you will train it to recognize patterns that are correlated with cats. And if you then give it this picture, it will say, okay, this thing looks furry, it has 2 eyes, it has 2 ears, I see some whiskers. So there's a high correlation that this is a cat, although everyone in this room will clearly see that this is not a cat because it doesn't have legs. So this is the state where all the AI hype is in. They're merely just a pattern recognizer, but these simple rules that are common knowledge to a human, there's no way to model this into a system like this. So please be aware that it's not magic in there. So we have this great tool that is actually a great pattern recognizer, and you can use it as such. But if you then look at the ecosystem of tools and frameworks out there to kind of develop these models, you end up with a huge space of frameworks. All the big companies are kind of pushing their own technology out there. You have TensorFlow from Google, PyTorch backed by Facebook, you have Microsoft CNTK, you have Amazon, which is pushing for MXNet. But if you really look at all those frameworks, it appears that they're just like an API, mostly a Python API, around some high-performance math libraries like BLAS or CUDA if you're using a GPU. So what it actually boils down to is that they're actually kind of offering you some API in some often more kind of a scripting language in order to train a model and execute it on some highly optimized math libraries. And if you look at how people use these tools nowadays, they call themselves then the data scientist. And the way that works is basically, so you start off with inspecting and cleaning up whatever data you get. And this is most often the most time-consuming part of your project is see what is this data and what can we get out of it. And then you kind of select and encode some features of the data or your desired outputs, because, for example, if you use a neural network, this typically expects just an array of floating points. So if you have an image, it's quite convenient how to convert it, but if you have text, you don't really know how to do it. So that's the second stage, is how can you make your raw data to something that can be consumed by these kind of machine learning models. And then the development starts, and this is basically scripting together some training procedure for finding out the model. And what it often boils down, it is looking for projects you have done in the past, or looking at the internet for scripts that do something pretty similar than what you want, and then you start scripting and adapting the data loading, and then you hope that it can consume the data set you have, and then you can hopefully get a model out of there. And then as in the cartoon, the stirring begins. So then you have to find your good hyperparameters, because training such a model is not deterministic. It depends on lots of parameters that you can tune, and even your random seeds. So sometimes you can have the exact same run with a different random seed, and you do significantly better or worse. So it's kind of a mix of experience and being lucky. But then in the end, you finally have your best performing model, and then your data scientists will happily dump this to the file system and say, these are the files that come out of whatever tool I'm using, here's your model. Great, but now, how can we use this in production? We just have some dump files in a file system that you know what it means, but we don't know. So how do we do this? And it's striking that all these frameworks that are out there that were on some slides ago, none of them really addresses the problem of how do you integrate this with whatever software you already have running. So if I do have to take one of the examples, then the most popular one is probably TensorFlow, and they have like the TensorFlow serving library, and this is how it looks like then. So they say, okay, if you have your model trained with TensorFlow, you can easily integrate it with your existing software. You just use a REST or gRPC. So gRPC is kind of a RPC protocol from Google, and this you then send to a server, which and this is all TensorFlow serving terminology. So I don't know what the dynamics are in the dynamic manager, for example, but they call it like that. So what happens is you do a REST request, you have something that's listening through a socket, parses your requests, then hands it over to this dynamic manager, which just selects one of your models that you have there, and then the loader is a thing that kind of reads the dump file from the file system and says, here's the model. And they have a very nice versioning scheme where they have subdirectories going from 1, 2, up to infinity, and every subdirectory is basically a version. So at least they have like an incremental version number that's at least something. And then how can you use this? Well, they provide a Docker container, and you say, okay, the only thing we need from you is this file system directory. So you provide this as a volume to your Docker container, and there you go. You can query your model, and you can happily use it in production. Yay. So let's check the boxes. So if you want to query your model only using an RPC or a REST call, if you train your models using TensorFlow, if you deploy your models on a containerized infrastructure, and if you don't need any additional metadata about the thing that your data scientist trained, beside this single incrementing integer, then you're basically done. If that's sufficient for you, you can leave the room, because then basically your problem is already solved. If that's not the case, then I invite you to stay, because then OSGi can help you. And it can help you in a number of ways. First of all, it can offer you a unit of deployment. In just having this dump file on a file system, you can just package it in a jar. And by doing so, you can just put it in a repository and at least have it archived somewhere. You can consume it from the repository wherever you need it. So it already gives you some more flexibility on how you can use the thing. Second of all, because you have this jar, you can also add these nice requirements and capabilities and really make it a resolvable artifact. So requirements could be like, hey, this is a machine learning model and you need these kinds of operations on your system to be able to run it. You need to know how to do a matrix multiplication, for example. So you can kind of use it to, which are the bits and pieces I really need on my runtime to be able to get some output out of this. And you can also assign some capabilities and say, hey, I'm a machine learning model and I know how to recognize cats, for example. And the thing I expect is inputs that are like an image of 3 dimensions or 100 by 100 pixels, for example. And at least then you know as a consumer what the thing is supposed to do. And you can resolve it in your application and say, for my application, I need a face recognition model so I can just resolve it against my repository that my data scientists provide me and figure out which is the best matching model for my application. Then it also gives you a lightweight service model. You can just offer your model as an OSGi service, and then you can still decide whether you just use it within the application or you expose it as a REST service or some other protocol, whatever is used inside your company. You have all the flexibility you want. We just provide you with a service. You can consume it however you want. And also, you can add additional properties on the service using the service properties, which make sure that you can actually filter if there are many models deployed on your current system. You can select at runtime which one matches best with your needs at that moment. Now, of course, if we want to implement such a system, there are still 2 things that we are missing. First of all, we need to be able to read the DUM file that your data scientist gave you, and depending the tool he gave you, this might be some different format. It might even be some closed format that you don't really know what's in there. And one thing that can help there is the Open Neural Network Exchange format. It's kind of an initiative to actually develop a common format for describing these kind of computation graphs. They define it as protocol buffers. And the good thing is that a lot of these frameworks either support it out of the box or somebody of the community actually did the effort to create a converter for whatever format is there. So you can probably import and export from most of the frameworks out there. Of course, the second thing we need is something that we can actually run this inside an OSGi environment. And when we shifted from doing distributed computing to AI, I actually found it a good idea to make a deep learning framework in OSGi back in the days. It was 2014. TensorFlow was not really around back then, so we thought, yeah, why not build something in OSGi? So we actually have a prototype framework where you can deploy and train neural networks just using OSGi bundles to deploy this. And again, the low-level operations are actually using the same native libraries that all the other frameworks are using. So performance-wise, you're kind of on par with state-of-the-art because you just improve whatever NVIDIA implements in their latest GPU drivers, let's say. And basically, you get distributed deployments for free because you can, for example, just expose your OSGi services as remote services. Then you can do very complex setups where you can, in parallel, train lots of models. So it's very convenient. And we also added a web UI so we can actually inspect and visualize whatever model we have. So basically, we have all the ingredients to start playing around with it. So let's go for a quick demo. So what I have here is a simple DS component where I added a dependency on a neural network. So the neural network serves is basically how I expect to the system gives me a neural network instance, and I can also get the properties out there. So basically what I do is just print out whenever a neural network is in my system and whatever properties are on there. So how do I get my neural network? I have this Python script also here. And this is basically coming straight from the PyTorch tutorials. So basically what they do is they define their neural network. So it's kind of a convolutional neural network. You have 2 convolutional layers, some linear layers, blah, blah, blah. They use rectified linear units for those interested. This is then where the magic happens. So you do model.train. Yay. And here you have then the main, where you have all kinds of hyperparameters that will make or break the success of your framework. And this is typically the lines of code that you change if you have different data set for your problem. So in this case, they use the MNIST data set. It's a data set of recognizing handwritten digits. It's kind of the hello world of deep learning. And so then you go in the loop and you start training and testing against the test set. So the only thing I added is, let me check, here where I, instead of dumping some raw Python object, I actually export it to this ONIX format and call the file mnis.onix. Now, because it takes some time to train a model, I already did that, so this is what comes out. I have this ONIX file, which should contain this neural network I trained. So what we can do now is import that here. And you can see it actually, it does some printing out of whatever it finds in there. So you can see it has these convolutions and pooling and ReLU. So everything you saw basically in the model definition now comes out here as being part of the computation graph. And the next thing I will do is then export that as a jar. So basically I made a Go command. So I take this MNIST network and I will export it as, and package it as a jar. And all these other things is like additional metadata that I think is pretty useful. So I can say, I require digits that are like 28 by 28 pixels. The output size is 10 because it classifies from 0 to 9. And I trained on the MNIST dataset, and this is my first version I have. There we go. And what comes out then is, ta-da, a jar. And now I go install. And we have a bundle. So we have now installed this bundle containing a neural net. So if I now start it, ta-da, my DS component says, hey, it appears there's a neural network in the system, and it has this version. It expects these inputs and outputs. It's trained on the MNIST dataset, so I have all the metadata out there. So let's see what it learned. I was talking about the UI, so this is basically a UI that you can also use to kind of by dragging and dropping stuff, you can basically start building your own neural network this way. But because it's already deployed, it should be there, so it finds it, and this is then how it looks like. And you can immediately again see the structure that was there in the Python script. So you have the two convolution layers, you have the two linear layers, and so on. And then let's draw some samples from the data sets and see what comes out. There we go, it's a 0. So we can just start sampling, and it actually learned quite accurately how to classify these handwritten things. So, success. Now, I was also talking about doing research in robotics, so there's no presentation that you can do without showing a robot moving. So let's go to that. So this is basically a use case where we have a robot, and the task is to teach it to pick up an object. And basically what you can do is kind of you move it around and you record the positions every time where it should go. And then you can basically replay it to do like this pick and place operations, for example. Of course, the problem is then it only records the position. And you have to recall where the hell did you put the thing that it has to pick up, because else it doesn't know what it should do. So one of the use cases we're working at is we add a camera on the end effector, and during the demonstration we see the camera frame that the robot is looking at when the demonstrator actually shows him what to pick up. And instead of just recording positions, we train a neural network to use as a pattern recognizer and see the thing that is probably just down the end effector, that's probably the thing you want to pick up. So next time you have to pick something up and you see the thing slightly on a different location, just move to that location and pick it up. And if you then want to integrate that in an OSGi bundle, then you get something like this. And this is where really the fun starts, because now you can use all the nice R7 and R6 features of OSGi inside your application integrated with neural net. So for example, for this application, I need a camera, I need a neural network, and I need something to control my R. And the camera, I will use a push stream to feed the frames of the camera to my application. Does everybody know what the push stream is? Who knows what a push stream is? Okay, so in short, a push stream is basically mimicking the Java Streams API, but instead of iterating over a fixed collection, you basically have some entity that gives you new items to process as we go. For example, a camera will give you new frames of the camera as it's recording. And then you can iterate over that and use things like map, where you take the frame and you map it. First, we convert it to a tensor. So this is converting this to basically an array of floats. We forward this to the neural network, and what comes out is then mapped to something that the controller knows how to update the arm location. And then the controller will return whether it successfully grasped something or not. So if we match success, then we short circuit this method and we resolve the promise of a Boolean. So at the moment you call the grasp method, you get a promise to a Boolean, which is basically saying, at some point in the future, I will know whether the grasp was successful or not. But until then, I just give you this promise. And I promise you that sometime in the future, I will give you a Boolean saying true or false. And if we get here, then we will return true. If we don't get there, we will either return false, or we will time out and it will give an exception, I guess. But this really shows how you can really get most of it using all the OSGi specs. And then, of course, you're all dying to see what will happen then. And it actually knows now I should pick up this blue block. And if this blue block is on a different location, I will just move a bit to pick up the blue block. And if you put some different objects around it, like other colored blocks, I still know that the demonstrator clearly showed me to pick up the blue block. And because this is a closed loop system, even if the blue block starts moving, it will just, oh, I'll move together with it. And you can also do it the other way around. So instead of teaching it where to pick up something, you can also teach it where to place it. So for example, I teach it to drop the blue block in my hand. So it will pick up the blue block and say, I don't see a hand. I don't see a hand. Ah, there it is. So this shows how you can actually this shows how you can actually, just by using OSGi, the service model, with all the great specs out there, you can really improve whatever your data scientist dumps out of his framework and really leverage all the nice things, the requirement capability model, the service model, to create very nice applications and integrate with whatever product you already have running. So with that, I would like to end the presentation. Please don't forget to evaluate the sessions. Feedback is always important. And thank you for your attention. If you want to play around with my OSGi prototype, you can find more information there. And that's it for me. Yeah, and you're basically fighting the big companies that are all pushing their own framework to get some market share. And at the moment, it looks like it's either Google with TensorFlow and Facebook with PyTorch that are kind of winning at the moment. Yeah, but it's true, but it's hard to convince everyone. Also because in this community, they typically have a high Python background and skills. So it's hard to convince those people. On the other hand, I also think that, I forgot what I was going to say. I also think that it's hard to kind of push forward another model because it's like the story with the standards. We have 10 standards doing something, so we need to unify it. Now we have 11 standards kind of story. So it's hard to kind of pitch it as being the unified model. I don't know.